A paradox appears in the sky long before we need a telescope to notice it. On some mornings, while the western sky still holds the deep blue of night, a brilliant white point rises near the eastern horizon. In other seasons it appears after sunset, shining so brightly that many people mistake it for an approaching aircraft. The light seems quiet, familiar, and almost gentle. Yet it does not come from a gentle world. It is reflected by clouds that hide a surface hotter than Mercury, crushed beneath pressure strong enough to destroy most ordinary machines, and almost entirely without liquid water. This is Venus, the brightest planet in Earth's sky after the Sun and the Moon, and one of the most difficult worlds in the solar system to understand. The mystery does not come from distance. During favorable approaches, Venus comes closer to Earth than any other planet. What makes it mysterious is its dense atmosphere and its highly reflective cloud layers which conceal the surface completely. We can see Venus with remarkable clarity, yet our eyes cannot see through it. The contrast between appearance and reality has followed Venus through much of human history. Many cultures regarded it as a sign of dawn, or as a symbol of beauty, war, love, power, or renewal. Ancient observers recorded its cycles long before they understood that Earth was also a planet. For a time, the light seen before sunrise and the light seen after sunset were treated as two separate objects. Only after generations of careful observation did people recognize that both were the same wandering world moving inside Earth's orbit. Today we call Venus the morning star when it appears before dawn, and the evening star when it shines after sunset. These names describe where we see it, not two different identities. Venus never travels far from the Sun in our sky because its orbit lies closer to the Sun than Earth's orbit does. From our viewpoint, the planet alternates between the eastern and western sides of the Sun, producing periods of visibility that last for weeks or months. Under the right conditions, Venus is bright enough to cast a very faint shadow on dark ground. This brightness does not come from light produced by the planet itself. The upper clouds reflect most of the sunlight that reaches them, turning Venus into a brilliant white sphere in the twilight. The same clouds that make the planet so easy to see from far away also form the curtain that hides everything below. Through a telescope, Venus changes shape like the Moon. When it lies on the far side of the Sun from Earth, it appears almost full, but its apparent size is small. As it moves closer to us, it grows larger while narrowing into a thin crescent. This cycle of phases became one of the observations that transformed astronomy. In the early 17th century, Galileo Galilei saw that Venus passes through a complete set of phases that the traditional geocentric model could not explain. That observation did not end every debate by itself, but it showed that Venus moves around the Sun. Venus is the second planet from the Sun, orbiting at an average distance of nearly 108 million kilometers. Light takes about 6 minutes to travel from the Sun to the planet. The orbit of Venus is more nearly circular than the orbit of most planets, so the amount of energy it receives changes relatively little during a year. One journey around the Sun takes almost 225 Earth days. The planet travels along its orbit at an average speed of about 35 kilometers per second. From Earth, however, a more noticeable cycle is the time required for Venus to return to the same relative position with Earth and the Sun. This synodic cycle lasts almost 584 days. Many civilizations used it in calendars and rituals because the appearances and disappearances of Venus could be predicted with increasing accuracy. In size, Venus resembles Earth more closely than any other planet. Its diameter is about 12,100 kilometers, only a few percent smaller than Earth's. Its mass is about 82% of Earth's mass, and its surface gravity is close to 90%. If a person could stand safely on the surface of Venus, the sensation of weight would not be very different from standing on Earth. This similarity in size once led people to call Venus Earth's twin. Both worlds formed from rock and metal in the inner region of the protoplanetary disk. Both probably contain an iron-rich core, a silicate mantle, and a solid crust. Both are large enough to hold an atmosphere and preserve internal heat for billions of years. Yet from broadly similar beginnings, the two planets evolved toward almost opposite states. Earth has stable oceans, a water cycle, a climate that allows life to flourish, and a crust divided into moving plates. Venus today is almost completely dry. It is surrounded by a massive carbon dioxide atmosphere, clouds of sulfuric acid, and a surface temperature of about 465 degrees Celsius. The difference is not simply that one planet lies closer to the Sun. It involves the original supply of water, the behavior of clouds, rotation, geological activity, atmospheric escape, and the exchange of carbon between air and rock. Venus has no natural satellites and no rings. The absence of a large moon makes the history of its rotation more difficult to reconstruct. Some models suggest that enormous impacts change the direction of its spin. Other models give an important role to solar tides and to the long-term torque produced by the dense atmosphere. No single explanation yet accounts completely for why Venus rotates so slowly and in the opposite direction from most other planets. Viewed from above the northern side of the solar system, Earth and most planets rotate counterclockwise. Venus rotates the other way. This motion is known as retrograde rotation. A person standing on the surface, if the clouds ever opened enough to reveal the sky, would see the sun rise in the west and set in the east. Venus takes nearly 243 Earth days to complete one rotation relative to the distant stars. That is longer than a Venusian year. Because the planet spins opposite to the direction of its orbit, however, a solar day, measured from one sunrise to the next, lasts nearly 117 Earth days. Light and darkness replace one another very slowly, yet the surface does not experience the enormous day-to-night temperature changes found on Mercury. The reason lies in the atmosphere. An immense mass of gas surrounds Venus, absorbing heat, transporting energy, and keeping surface temperatures relatively uniform between day and night. Even though the night lasts for dozens of Earth days, the ground does not cool very much. The dense atmosphere behaves like an ocean of gas, continually redistributing heat around the planet. The rotation axis of Venus is almost completely overturned. Under the usual convention, its axial tilt is close to 177 degrees. If the planet is treated as rotating almost exactly upside down, the remaining tilt is only about 3 degrees. Venus, therefore, does not experience strong seasons caused by axial tilt as Earth does. The atmospheric variations we observe are linked mainly to cloud dynamics, waves, interactions with the Sun, and longer cycles that are not yet fully understood. The rotation is not perfectly steady like an ideal clock. Radar measurements made over several decades show that the length of a Venusian day changes slightly over time. The massive super-rotating atmosphere exchanges angular momentum with the solid planet, causing Venus to speed up or slow down by a tiny amount. The variation may reach about 20 minutes within a day, lasting hundreds of Earth days. Proportionally, this is very small, but it is large enough to complicate the precise targeting of future landers. About every 8 Earth years, the geometry of Venus, Earth, and the Sun nearly repeats. During that interval, there are 5 synodic cycles and almost 13 Venusian years. Venus therefore returns to similar regions of the sky in an easily recognized 8-year rhythm. Its rotation was once thought to be almost locked to its close approaches to Earth, but modern data show that the relationship is imperfect and influenced by the atmosphere. From outside, Venus appears creamy white or pale yellow. No continents, blue oceans, or mountain ranges are visible in ordinary light. Clouds hide the entire landscape. To understand the planet, we must do what human vision cannot. We must separate the atmosphere layer by layer, measure how light is absorbed, use radar to penetrate the clouds, and send instruments directly into an environment capable of destroying them. An imaginary descent toward Venus begins in the upper atmosphere, where atoms and molecules gradually thin into space. Here, ultraviolet radiation and the solar wind ionize the gas, creating an ionosphere. Venus does not possess a strong global magnetic field like Earth. Instead, the solar wind bends the Sun's magnetic field around the ionosphere, producing an induced magnetosphere and a tail that extends into the night side. This induced magnetosphere is not a sealed shield. Energy and particles from the Sun still interact with the upper atmosphere, knocking away ions and helping material escape into space. Yet atmospheric loss on Venus cannot be explained by the absence of an internal magnetic field alone. Gravity, temperature, atmospheric composition, volcanic replenishment, surface chemistry, and the changing radiation of the Sun all contribute. It is a connected system of many processes, not the result of a single cause. Deeper down, the atmosphere becomes dense very quickly. Carbon dioxide makes up about 96.5% of the gas. Most of the remainder is nitrogen, with traces of sulfur dioxide, carbon monoxide, water vapor, argon, helium, and other compounds. Nitrogen forms a smaller percentage than it does on Earth, but because the total atmosphere is so massive, Venus may contain more nitrogen in absolute terms than Earth's atmosphere does. At the surface, the pressure is about 92 times the pressure at sea level on Earth. This is comparable to the pressure beneath nearly 1 kilometer of ocean water. The lower atmosphere is so dense that it no longer resembles the thin air familiar to us. It remains a gas, but its density creates powerful drag, changes the way sound travels, and allows small particles to remain suspended longer before falling. Under surface conditions, carbon dioxide lies above both its critical temperature and its critical pressure. The lowest atmosphere, therefore, has some properties of a supercritical fluid. There is no clear boundary between gas and liquid, yet the material still flows around the terrain. This does not turn the surface into an ocean of carbon dioxide. It means that the surrounding substance is dense and transfers heat, force, and sound in ways very different from air on Earth. The average surface temperature is about 465 degrees Celsius, hotter than Mercury, even though Venus lies farther from the Sun. That temperature is high enough to melt lead and weaken many metals. The surface, however, is not a global sea of lava. Most of the rock remains solid, slowly baked under extreme pressure and harsh chemical conditions. The extreme heat is often summarized as the greenhouse effect, but the real process is more complex than a single phrase suggests. The surface absorbs part of the incoming sunlight and releases energy as infrared radiation. Carbon dioxide and other gases absorb many infrared wavelengths, radiate energy in every direction, and force heat to pass through layer after layer before it can escape to space. Great pressure broadens the absorption bands, while constant molecular collisions increase the atmosphere's ability to trap heat. Temperature also rises with depth because the gas is compressed. In a thick atmosphere, a parcel of descending air encounters greater pressure and warms according to thermodynamic principles. The Venusian surface is therefore not hot merely because carbon dioxide is present. The entire enormous column of atmosphere creates a deep thermal structure. The greenhouse effect controls how much heat is retained, while adiabatic compression helps explain why the lower atmosphere becomes so extraordinarily hot. The upper clouds reflect most incoming sunlight, giving Venus a high albedo. If we consider only absorbed energy, the planet does not receive vastly more than Earth, in the simple proportion that distance might suggest. The crucial point is that absorbed energy has great difficulty escaping. A world covered by bright clouds can still possess a furnace-like surface when the gas below is thick enough and absorbs infrared radiation strongly. Between about 48 and nearly 70 kilometers above the surface lies a multi-layered cloud system. The droplets consist mainly of sulfuric acid mixed with a small amount of water. They do not fall all the way down to form oceans of acid. As the droplets descend into warmer regions, they evaporate. Sulfur-bearing molecules continue through chemical reactions and are eventually transported upward again. The clouds of Venus are an active chemical cycle, not a fixed layer of material. Measurements show that cloud particles do not all have the same size. Fine haze particles mix with larger droplets, usually divided into several size groups. The largest particles remain controversial because their shapes and compositions are not known with confidence. Particle size affects how quickly droplets fall, how much light they reflect, and how chemicals move between atmospheric layers. Sulfur dioxide plays a central role in this cycle. The gas rises from lower levels with long-term sources in rock and volcanic activity, and ultraviolet light converts it into other sulfur compounds. Those compounds combine with water to form sulfuric acid. Because sulfur dioxide is destroyed in the upper clouds on timescales far shorter than the age of the planet, changes in its abundance may reveal atmospheric transport or renewed supply from below. At altitudes of about 50 to 60 kilometers, temperature and pressure approach ranges more familiar from Earth. This is why the cloud layer often appears in proposals for balloon exploration. A vehicle filled with a lighter gas could float without wings, using the dense atmosphere to remain aloft for weeks or months. Yet familiar temperature and pressure do not make the environment safe. The surrounding gas contains almost no breathable oxygen. The cloud droplets are intensely acidic. Available water is extremely scarce, and ultraviolet radiation is severe at higher levels. Materials must resist corrosion, electronics require protection, and vehicles must endure continuous high winds. The cloud layer is easier to explore than the surface, but it is not an Earth-like refuge. The clouds of Venus circle the planet far faster than the solid ground rotates. Near the cloud tops, the atmosphere may complete one journey around Venus in only about 4 Earth days, while the surface requires nearly 243 days to rotate. This is atmospheric superrotation. Upper-level winds reach hundreds of kilometers per hour and carry bands of cloud around the entire planet. Superrotation is one of the major problems in planetary meteorology. Uneven solar heating produces thermal tides and systems of atmospheric waves. These waves transport angular momentum both horizontally and vertically. Interactions among the equator, middle latitudes, polar regions, and the terrain below help the atmosphere maintain its high speed. Modern models reproduce many observed features, but they do not yet explain completely how the system began or how it remained stable over long periods. Japan's Akatsuki spacecraft provided some of the most important observations of this mechanism. Its data indicate that atmospheric waves and thermal tides transport angular momentum toward the equator, helping to accelerate the flow. The mission also discovered an enormous bow-shaped structure that remained almost stationary relative to the surface while the surrounding clouds raced past at great speed. The bow-shaped structure is an atmospheric gravity wave formed as winds pass over high mountains. The terrain forces the air to rise and fall, creating oscillations that travel upward to the cloud tops. The wave extends for thousands of kilometers and is considered one of the largest mountain waves ever observed in the solar system. Its discovery shows that the surface still influences the upper atmosphere, even through tens of kilometers of dense gas. In ultraviolet light, Venus is no longer a featureless white sphere. The cloud tops reveal bright and dark bands, Y-shaped patterns, spirals, and regions that change within only a few days. The darker areas absorb ultraviolet radiation more strongly, but the substance responsible has not been identified with certainty. Candidates include sulfur compounds, iron chloride, tiny mineral particles, and incompletely understood products of photochemistry. The ultraviolet absorber plays a climatic role because it determines how much solar energy is retained within the cloud layer. If its composition or distribution changes, atmospheric temperature and circulation may change as well. Identifying this material is therefore more than a chemical puzzle. It is also a key to understanding the energy budget of the entire planet. At both poles, the atmosphere forms enormous vortices. The southern polar vortex has been observed changing from an almost circular shape into elongated, double-lobed, and more complex forms. Inside the vortex, air moves through layers with different temperatures and altitudes. Unlike the eye of a hurricane on Earth, this structure is not connected to an ocean or to rainfall. It is maintained by global circulation and the distribution of angular momentum through the atmosphere. The night side of Venus also glows faintly at certain wavelengths. Oxygen atoms created when carbon dioxide is broken apart on the day side can be carried by winds into darkness. There, they recombine and emit a weak glow known as airglow. Nitric oxide and other compounds produce additional bands of emission. The light is far too faint for human eyes to see from the surface, but it reveals how material is transported around the planet. Venus has weather, although it is unlike weather on Earth. There is no cycle of water rain, no rivers, and no tropical storms. Instead, there are waves, vortices, convection, chemical changes, acid clouds, thermal tides, and super-rotating winds. These phenomena occur in a system with almost no ocean and no cool surface capable of absorbing heat from one season to the next. Lightning on Venus remains a subject of debate. Several probes and orbiters have recorded radio or electromagnetic signals that may have come from electrical discharges. Other observations have not detected flashes at the rate expected if lightning were as common as it is on Earth. Volcanic ash, collisions among cloud particles, and plasma interference can all produce signals that are difficult to distinguish. Until several instruments make simultaneous measurements, the true frequency of lightning will remain uncertain. If lightning exists, the mechanism that separates electric charge must differ from the process inside water clouds on Earth. Acid droplets, sulfur particles, crystals, or volcanic dust may collide and exchange charge. Yet the Venusian clouds contain very little water, temperature, and pressure change across many layers, and the particle composition is not known in enough detail. This is a clear example of how a familiar phenomenon may require an entirely different explanation on another planet. Sound in the lower atmosphere would also be unfamiliar. Dense carbon dioxide changes both the speed at which sound travels and the way different frequencies are absorbed. A voice produced by a functioning speaker would sound deeper and more distorted than it does on Earth. Winds near the surface are usually slow, but the high density of the gas gives them considerable force. A breeze moving only a few kilometers per hour could still push dust or shake lightweight components. The dense atmosphere also slows falling objects after their initial deceleration. This helps descending probes. Although heat and pressure are dangerous, atmospheric drag allows a spacecraft to approach the ground without keeping a large parachute open all the way to the surface. The same density lets weak winds transport fine sand and dust, producing streaks and small deposits that radar can detect. Light at the surface is much dimmer than above the clouds. Radiation scatters through the thick atmosphere, producing the yellow-orange sky seen in images from Soviet landers. There is no sharply defined sun shining in a blue sky. Atmospheric haze softens the horizon, and distant objects quickly lose contrast. Refraction within the dense air also bends the path of light. The apparent positions of the horizon and the sun would differ from simple geometry, especially when light travels close to the ground. A hypothetical observer might see the landscape compressed, stretched, or blurred by layers of air at different temperatures. If humans could stand safely on Venus, the landscape would not look like a literal inferno of open flame. Most surface rocks would not glow red, and no ocean of fire would surround the observer. The sense of danger would come from the stillness, the constant heat, the invisible pressure, and a sky that never becomes clear. Machines would heat slowly until insulation, batteries, soldered connections, and electronic components stopped working. These conditions make landing exceptionally difficult. A spacecraft must survive sulfuric acid clouds, slow down through dense gas, endure rapidly increasing pressure, and release heat into an environment hotter than an industrial furnace. The successful Venera landers relied on strong pressure vessels, insulation, and relatively simple systems. Even then, most operated for only a few dozen minutes to a little more than 2 hours after reaching the ground. A modern vehicle designed to survive longer would need one of two technological approaches. The first would isolate and actively cool its electronics. The second would use high-temperature semiconductor components capable of operating directly in Venusian conditions. The second approach might allow small stations to survive for weeks or months, although their computing power would be more limited than that of conventional machines. Before planning a long-lived station, scientists must know more precisely what the surface is made of. The clouds make ordinary orbital cameras almost useless for studying terrain. Radar is the primary tool because radio waves pass through the clouds, reflect from rock, and return to a spacecraft. The strength of the return depends on roughness, slope, composition, and electrical properties. A radar image is not a photograph in the way the human eye understands one. A bright region may be a slope facing the spacecraft, rough rock, or material that reflects radio waves strongly. A dark region may be flat, smooth, or tilted away from the radar. Interpreting a map of Venus therefore requires several viewing angles, elevation measurements, gravity data, and geological models. The present atmosphere is only the final state of a very long history. The most important question is not how hot Venus is today, but when it became so hot. Did a planet almost the size of Earth ever possess rain, rivers, or seas? If water once existed, did it disappear early, or did it survive long enough to support a stable climate for a meaningful period? Venus today contains very little water vapor. If all atmospheric water were condensed onto the surface, the resulting layer would be extremely thin compared with Earth's oceans. Yet the ratio of deuterium, the heavy form of hydrogen, to ordinary hydrogen in the Venusian atmosphere is more than 100 times the corresponding ratio on Earth. Lighter hydrogen escapes more easily into space, leaving the remainder enriched in deuterium. This isotopic signature indicates that Venus lost a substantial amount of water. The deuterium ratio does not tell us directly how deep an ancient ocean might have been. It depends on the original water supply, the rate of atmospheric escape, volcanic replenishment, and the way the atmosphere mixed over time. Even so, it is strong evidence that young Venus was wetter than the planet is today. One pathway toward water loss begins with a moist greenhouse. As the surface warms, more water vapor enters the atmosphere. The upper atmosphere becomes wetter, allowing ultraviolet radiation to break apart increasing numbers of water molecules. Hydrogen escapes into space while oxygen remains behind for a time. If the process continues, the water inventory declines even before every ocean has completely evaporated. In a runaway greenhouse state, the absorbed solar energy exceeds the maximum rate at which an ocean-bearing planet can release heat to space. Evaporating water strengthens the greenhouse effect, temperature rises further, and the self-reinforcing process continues until the oceans become vapor. This need not occur as one sudden event. It may unfold through several stages and may be strongly influenced by clouds and geological activity. The young Sun was dimmer than it is today by several tens of percent. This opens the possibility that Venus was once cooler despite its proximity to the star. Some climate models show that a slowly rotating planet could develop a thick cloud shield over its permanent or long-lasting dayside. Such clouds would reflect sunlight strongly, protecting the surface from extreme heating and allowing liquid water to survive longer than distance alone would suggest. The result, however, depends strongly on topography, water abundance, atmospheric composition, and the planet's past rotation rate. If young Venus rotated faster, its clouds would have been distributed differently. If it possessed only shallow seas or scattered lakes, the cooling effect would change. If the early atmosphere already contained large amounts of carbon dioxide, the surface may have become hot much sooner. Another family of models suggests that Venus never developed long-lived oceans at all. After the planet formed, heat from impacts and radioactive decay created a magma ocean. Water vapor and carbon dioxide escaped from the molten rock, forming a thick atmosphere. If solar radiation prevented the surface from cooling enough for water vapor to condense, water may have been lost to space while the planet was still extremely hot. Both histories lead to the dry Venus we see today, but they leave different evidence behind. A planet that once held oceans would have experienced weathering, sediment transport, and chemical exchange between water and rock. A planet that never condensed widespread water would preserve a different pattern of noble gases and isotopes. This is why direct measurements deep in the atmosphere are so valuable. Noble gases such as neon, argon, krypton, and xenon take almost no part in ordinary chemical reactions. Their isotopic ratios record where the atmosphere came from, what material was added, and how much gas escaped. Earlier measurements were not precise enough for every member of this group. A modern probe descending from the upper atmosphere toward the ground could read the surviving pages of atmospheric history one by one. Argon-40 is especially useful because it is produced by the radioactive decay of potassium-40 in rock. The amount of argon-40 released into the atmosphere reflects how extensively the planet has outgassed from its interior. Combined with measurements of xenon and krypton, it could distinguish a Venus that released most of its gases early from one that continued outgassing through many geological stages. Oxygen created when water is split apart presents another question. If Venus lost an entire ocean, an enormous amount of oxygen had to be removed. Some escaped into space, some probably reacted with iron-rich rocks or was carried into the mantle through geological processes. The present atmosphere does not contain the free oxygen expected from a vanished ocean, which means that the surface and interior must have played important roles. On Earth, the long-term carbon cycle helps regulate climate. Carbon dioxide dissolves in water, participates in rock weathering, moves into the oceans, and is eventually stored in carbonate minerals. Plate tectonics carries some carbon back into the mantle, while volcanoes release part of it again. This cycle does not hold temperature perfectly constant, but it creates a feedback system that operates over millions of years. Venus has no present ocean, and no global system of plate tectonics has been detected. Carbon is not removed from the atmosphere through the same pathway. An enormous quantity now remains in the air as carbon dioxide instead of being widely transferred into near-surface carbonate rocks, as it is through Earth's carbon cycle. This difference helps maintain the planet's extreme pressure and temperature. Even so, reactions between gas and rock continue. Surface minerals may oxidize, combine with sulfur, and transform under intense heat. Carbon dioxide, sulfur dioxide, and trace gases enter cracks, react with fresh lava, and alter composition over time. We do not know how quickly these processes occur because no laboratory has operated on the surface for an extended period. The geology and climate of Venus therefore cannot be separated. Volcanoes release carbon dioxide, sulfur dioxide, water vapor, and noble gases. The atmosphere controls surface temperature and influences both crustal strength and mineral chemistry. Changes in the crust determine whether gases are stored, recycled, or released. Venus is a connected system from its core to its clouds. The absence of an internal magnetic field is also linked indirectly to the planet's thermal history. A global magnetic field requires suitable motion within an electrically conducting metallic core. Venus rotates slowly, but slow rotation alone does not explain why a dynamo is absent. The core may not have cooled rapidly enough to produce strong convection, or it may contain stable layers that prevent vigorous motion. Earth cools its interior through mantle circulation and plate tectonics. If Venus operates beneath a stagnant lid or through localized recycling, heat flow from the core would be different. The core may still be liquid without generating a global magnetic field. Only precise measurements of gravity, rotation, and tidal response can place strong limits on the deep interior. The possibility that Venus once possessed water makes it central to the concept of a habitable zone around a star. The habitable zone is often described as the range of distances where liquid water could exist on a surface. Distance, however, is only the beginning. Clouds, rotation, pressure, atmospheric composition, topography, oceans, and geological activity determine the path a real planet follows. Venus lies close to the inner edge of the region where liquid water may once have been possible. If the planet maintained a temperate climate for hundreds of millions of years, then the boundary of habitability is not a fixed line. If Venus was hot from the beginning, a different group of models becomes more likely. In either case, Venus is our nearest test of how we evaluate thousands of rocky planets orbiting other stars. An Earth-sized exoplanet close to its star may resemble Venus more than Earth. Seen from a great distance, bright clouds could hide the surface, while a thick carbon dioxide atmosphere might produce a spectrum that is easy to misinterpret when data are limited. Understanding Venus helps scientists recognize the signatures of extreme greenhouse warming, water loss, and an atmosphere shaped by intense photochemistry. Venus also reminds us that one unusual signal is rarely enough to demonstrate life. Oxygen, methane, sulfur dioxide, or any unexpected compound must be interpreted within the context of climate, geology, and photochemistry. A planet is not a motionless test tube. Volcanoes, ultraviolet radiation, minerals, and atmospheric circulation can produce molecules that are often associated with biology on Earth. The debate over phosphine in the Venusian atmosphere illustrates this problem clearly. In 2020, a research team reported a radio signal interpreted as phosphine within the clouds. On Earth, this compound is associated with industry and with certain oxygen-poor environments containing microorganisms. The report quickly encouraged speculation about life in the cloud layer. Later, analyses raised questions about data processing, instrument calibration, and whether sulfur dioxide could produce a similar signal. Some groups did not detect phosphine at all. Others argued that, if it exists, its abundance is lower than first reported or changes over time. Phosphine has not been confirmed as evidence of biology. Even if the compound were detected beyond doubt, its origin would still require investigation. Unknown photochemical reactions, minerals lifted from the surface, lightning, volcanism, or chemistry inside cloud droplets would all have to be examined before a biological conclusion could be considered. Science does not end when a molecule is identified. The decisive question is which process can produce it at the observed rate. Temperature and pressure in the cloud layer are relatively moderate, but water presents a severe obstacle. Studies of water activity indicate that sulfuric acid droplets on Venus are drier than the limit tolerated by any known life on Earth. Their acidity also exceeds that of most familiar biological environments. Hypothetical life would require profoundly different cellular chemistry or unmeasured microscopic regions with more favorable conditions. The possibility of present-day life in the clouds is therefore considered low, but that is not a reason to stop exploring them. Studying cloud particles can reveal the ultraviolet absorber, the sulfur cycle, the movement of minerals, and the planet's tiny remaining water supply. A completely non-biological result would still be deeply valuable because it would expand our knowledge of the chemistry possible in planetary atmospheres. Direct cloud samples would resolve many uncertainties that remote observations cannot. Droplet size, elemental composition, isotopic ratios, and particle structure reveal how cloud material forms. If solid particles act as condensation nuclei, they may come from meteoritic dust, volcanic material, or minerals lifted by winds from below. A balloon carried by the wind could observe the clouds for much longer than a falling probe. It could measure changes between day and night, across latitudes, and among different atmospheric layers. The two Vega balloons demonstrated that this approach was possible when they traveled through the Venusian atmosphere for almost 2 Earth days. Modern technology could extend the operating time and adjust altitude to sample several environments. Venus offers no simple answer to whether a planet is habitable. It shows that habitability is a changing state, maintained or lost through interactions among water, rock, gas, and starlight. A world nearly identical to Earth in size can become profoundly alien when climate feedbacks cross a critical threshold. To learn when Venus crossed that threshold, we must search the surface for evidence. Ancient rocks may preserve records of water, early crustal composition, and past volcanic eras. Yet the clouds hide the planet, and lava, together with geological deformation, has rewritten much of the terrain. The oldest surviving pages remain exposed only in certain highland regions. The Magellan spacecraft completely changed the human view of Venus. From 1990 until 1994, its radar mapped nearly the entire planet in unprecedented detail. The white clouds disappeared from the radio data, revealing a world of lava plains, volcanoes, mountain ranges, canyons, domes, and structures with no exact counterpart on Earth. Broad volcanic plains cover much of the Venusian surface. Lava from many periods overlaps, filling lowlands and surrounding older terrain. Some plains appear extremely smooth in radar images, while others are crossed by wrinkle ridges, fractures, or long flows. Venus is not a uniform sphere covered by a single planetary eruption. The two largest highland regions are Ishtar Terra in the northern hemisphere and Aphrodite Terra, which extends near the equator. Ishtar Terra is similar in size to a small terrestrial continent and contains the plateau of Lakshmi Planum and the Maxwell Montes mountain range. Aphrodite Terra stretches for thousands of kilometers and includes regions shaped by extension, compression, and volcanism at different times. Maxwell Montes is the highest mountain range on Venus, rising about 11 kilometers above the planet's mean radius. Its elevation produces lower pressure and cooler temperatures than the surrounding plains, although conditions remain extremely hot by Earth standards. Radar shows that many high peaks reflect unusually strongly, producing bright areas that resemble snow cover in radio images. The phrase metallic snow is sometimes used for this high-altitude coating, but it should not be understood as ordinary snow. Its composition remains uncertain. Metal-bearing compounds or minerals whose electrical conductivity changes with temperature may condense or become stable at high elevations. Future radar and infrared spectroscopy will test these explanations. Among the most important terrains are the tesserae, highland regions cut by intersecting networks of ridges and grooves. The word tessera comes from the small stones used in mosaics because radar images make these surfaces resemble complex pieces fitted together. Tesserae usually stand above the surrounding plains and are considered among the oldest exposed terrains on Venus. The tesserae may preserve evidence of crust unlike the basalt common across the plains. If they contain silica-rich rock, that material may have formed through processes involving water or through prolonged crustal recycling. Present infrared emissivity data, however, are not precise enough to identify their minerals with confidence. Tesserae may be remnants of ancient crust, compressed plateaus, or products of a geological mechanism unique to Venus. Alpha Regio is a famous tessera region and a target for the Da Vinci descent probe. As the probe drops below the clouds, its camera will image the terrain at steadily improving resolution. The shapes of slopes, rock layers, and possible erosion features may reveal whether this landscape once interacted with water or formed under completely dry conditions. Beyond the tesserae are hundreds of coronae, nearly circular or oval structures, commonly surrounded by rings of fractures and troughs. They range from a few dozen to more than 1,000 kilometers across. Most are interpreted as places where hot mantle material rose upward, lifted the lithosphere, and caused the surface to swell, crack, or collapse. Beyond the tesserae are hundreds of coronae, nearly circular or oval structures commonly surrounded by rings of fractures and troughs. They range from a few dozen to more than 1,000 kilometers across. Most are interpreted as places where hot mantle material rose upward, lifted the lithosphere, and caused the surface to swell, crack, or collapse. Coronae demonstrate that the crust of Venus is not motionless. Gravity and topographic data show that many coronae are underlain by anomalies consistent with hot, buoyant material rising from the mantle. Research published in 2025 identified numerous structures that appear to be undergoing continued deformation driven by processes below. Venus lacks global plate tectonics, but localized tectonic activity seems to continue. Some coronae show the crust being stretched and thinned. Others may mark places where cooler, denser material sinks into the mantle. This is not full plate subduction of the kind found on Earth, but it may represent regional crustal recycling. Such a process would allow Venus to return surface material to its interior without a continuous global network of moving plates. New models of crustal thickness also change the picture. Research supported by the National Aeronautics and Space Administration suggests that the Venusian crust averages about 40 kilometers in thickness and rarely exceeds about 65 kilometers. As the crust grows thicker, rocks at its base experience greater heat and pressure, become denser, detach from the upper crust, or partially melt again. Metamorphism, delamination, and remelting may prevent the crust from thickening without limit. Material returns to the mantle, while new magma rises to feed volcanoes. If this model is correct, Venus possesses a quiet recycling system beneath the surface. It differs from plate tectonics, yet still exchanges material between crust and mantle. Volcanism dominates the landscape. Tens of thousands of volcanic structures have been identified, from small cones to enormous mountains, hundreds of kilometers wide. Many have gentle slopes because their lava traveled far, resembling shield volcanoes on Earth, but often reaching much greater size. Martmons, Sifmons, and Ozimons are prominent examples. Pancake domes are another unusual landform. They have broad, relatively flat tops, steep sides, and diameters of tens of kilometers. Their shape suggests lava more viscous than ordinary basalt, pushed upward and spreading slowly across the surface. Their exact composition is unknown, but they show that Venusian magma has not always possessed the same physical properties. Long lava channels such as Baltis Vallis extend for thousands of kilometers, farther than any single lava flow known on Earth. To travel such distances, the lava must have been extremely fluid, erupted rapidly, well insulated, or influenced by several of these factors at once. Some channels curve like rivers, but molten rock rather than water carved them. For decades, scientists debated whether volcanoes were still active on Venus. Changing sulfur dioxide, infrared hotspots, and young-looking terrain all suggested recent activity, but none provided direct proof. The turning point came when Magellan radar images of the same regions, acquired at different times, were compared with great care. At Mart Mons, a volcanic vent changed shape and expanded noticeably during about 8 months in 1991. Models of viewing geometry and terrain showed that an eruption was the best explanation. Lava appears to have filled the vent and spilled down the slope. This became the first direct evidence of active volcanism during the Magellan mission. An analysis published in 2024 found additional changes at Sif Mons and in Niobe Planitia. Radar reflectivity increased in patterns consistent with fresh lava flows appearing between 2 observations. After differences in viewing angle and instrument noise were excluded, the researchers concluded that both regions probably erupted during the early 1990s. These discoveries do not mean that all of Venus is erupting continuously. They show that volcanism may be common enough for a spacecraft observing the planet for only a few years to detect multiple changes. If Venus is active at even a substantial fraction of Earth's level, volcanic gases are still adding sulfur dioxide, carbon dioxide, and water vapor to the atmosphere. Modern volcanism matters because it connects the interior with the climate. A large eruption that carries sulfur into the clouds could alter the planet's reflectivity for a limited time. Carbon dioxide remains much longer. On a world without oceans to absorb gases, every volcanic era contributes to atmospheric history in a way different from Earth. Venus can no longer be described simply as a planet that experienced one catastrophic resurfacing event and then became quiet. The relatively even distribution of impact craters once led to the idea that most of the crust was renewed during a short interval several 100 million years ago. Terrain, lava flows, and deformation now suggest a more complicated history, with different regions remaining active at different times. Some areas were probably resurfaced rapidly by widespread lava. Other regions preserved ancient tesserae. Coronae, rift zones, and crustal blocks continued to deform during separate periods. The present surface is the overlapping result of many stages, not a map created in a single event. Impact craters provide a relative clock for this history. Venus has fewer craters than the Moon or Mars because its surface is younger, and its dense atmosphere prevents many small objects from reaching the ground. Small meteoroids burn up or break into clusters, producing groups of pits rather than one simple crater. Only sufficiently large bodies cross the atmosphere with most of their energy intact. Many impact craters have sharp rims and ejecta that show little erosion. No rain, rivers, or glaciers destroy them. The dense atmosphere, however, allows shock waves to spread across the ground, while lava and deformation can bury older structures. Crater distribution suggests an average surface age of several 100 million years, although the uncertainty remains large. Chemical erosion and thermal weathering still occur. Rocks exposed to sulfur-bearing gases and carbon dioxide at high temperature may develop new mineral coatings. The day-to-night thermal cycle is smaller than on Mercury, but it is extremely long. Slow winds move fine particles across the surface, while volcanism covers older rocks with fresh material. Venus does not possess an unchanging landscape. It simply lacks the familiar agents of erosion found on Earth. The Venera landers measured rock composition at several lowland sites and found results broadly consistent with basalt. This agrees with the planet's widespread volcanic plains. Yet the landing sites represent only low elevations and tell us nothing directly about the composition of tesserae or high plateaus. Sampling a few lava fields and then trying to infer the geology of all Earth would have the same limitation. Several infrared windows in the atmosphere allow radiation from the surface to escape. Venus Express and Akatsuki observed the night side through these wavelengths, searching for emissivity differences that might reveal rock composition or recently formed surfaces. Clouds, temperature, and the atmosphere itself create strong interference, making mineral identification difficult. A new generation of radar will provide higher resolution and more reliable comparisons over time. Interferometric radar measures changes in the phase of reflected waves and may detect surface deformation far smaller than anything visible in Magellan images. If volcanoes inflate the ground, faults shift, or coronae continue to change, future missions may record those processes directly. Gravity also reveals the interior. When a spacecraft passes over a region with slightly greater mass, its speed changes by a tiny amount. Tracking radio signals maps gravity anomalies, helps estimate crustal thickness, and shows how topography is supported. A high plateau with only a small gravity anomaly may have a deep crustal root, much as continents float on the mantle of Earth. Venus probably has an iron-rich core, a rocky mantle, and a crust, but the size of the core has not been measured precisely. With no long-lived seismometer on the surface, scientists must infer the interior from mass, moment of inertia, gravity, and tides. The planet's response to the gravitational pull of the Sun contains information about whether the core is liquid or solid. Internal heat escapes through pathways different from those on Earth. There is no global network of mid-ocean ridges and subduction zones. Heat may accumulate beneath the lithosphere and then escape through volcanic episodes, mantle plumes, coronae, and broad deformation. Such a system could produce periods of intense activity separated by quieter intervals. High surface temperature places the upper crust under conditions unlike those on Earth. Rock becomes softer at shallower depths, affecting the way mountains rise and faults develop. Maxwell Montes may be supported by thickened crust, horizontal compression, mantle flow, or a combination of mechanisms. Current data are not detailed enough to select one explanation. The lack of water within the rock also changes its mechanical behavior. Water lowers melting temperatures and helps minerals deform more easily. A dry Venusian mantle may be stronger in certain ways, although high temperature tends to weaken it. The balance between dryness and heat determines whether the crust breaks into plates, bends, or recycles locally. A seismometer on the surface would answer many questions, but surviving the heat for a long time is a major challenge. Another idea is to use balloons to measure pressure waves produced by earthquakes. On Earth, large earthquakes send low-frequency sound into the upper atmosphere. Because the Venusian atmosphere is denser, this method may be especially sensitive to ground motion. A network of balloons and orbiters could detect the same event in several ways: pressure waves in the atmosphere, thermal changes at the surface, and newly released volcanic gases. Such a system would transform Venus from a static geological image into a planet monitored through time. We would no longer ask only when a landscape formed. We could watch it change. Humanity required thousands of years to move from seeing Venus as a light in the sky to hearing its winds and viewing rocks on its surface. The journey was not direct. Many spacecraft failed before leaving Earth, lost contact on the way, or were destroyed by the atmosphere. Each failure forced engineers to learn more about an environment they had never encountered before. In European tradition, the name Venus comes from the Roman goddess of love and beauty, equivalent to Aphrodite in Greek mythology. Other cultures gave the planet different names and meanings. Babylonian records connected it with the goddess Ishtar. Maya astronomers followed its cycle with remarkable precision and incorporated it into ceremonial calendars and political calculations. The ability to predict the appearances of Venus did not mean that people understood it as a physical world. For centuries, the planet remained only a point of light moving across the celestial sphere. Telescopes revealed its phases, but clouds concealed the surface. Some observers mistook faint atmospheric markings for solid terrain and tried to measure the rotation period producing conflicting results. Transits of Venus across the Sun once became some of the largest international scientific events in history. When Earth, Venus, and the Sun align precisely enough, the planet appears as a small black point moving across the solar disk. Transits occur in pairs, separated by 8 years, followed by gaps lasting more than a century. During the 18th and 19th centuries, expeditions traveled around the world to observe the moments when Venus touched the edge of the Sun. By comparing observations from widely separated locations, astronomers hoped to measure parallax and calculate the distance from Earth to the Sun. Storms, disease, war, inaccurate clocks, and the black drop effect made the work harder than expected, but the campaigns helped create a global scientific network. During the transit of 1761, Mikhail Lomonosov observed a glow around Venus and concluded that the planet possessed an atmosphere. The historical interpretation of his observation is still discussed, but the central idea was correct. Venus is not a bare sphere like the Moon. It is surrounded by an atmosphere denser than that of any other rocky planet. By the 20th century, radar made it possible to measure rotation through the clouds. Radio signals were transmitted toward Venus and reflected back to Earth. Frequency shifts across opposite sides of the planetary disk showed that Venus rotates extremely slowly and in the retrograde direction. One of the planet's most basic properties was not established with confidence until the space age had begun. The first attempts to send spacecraft toward Venus revealed the difficulty of early space engineering. Many Soviet craft in the Venera program failed to leave Earth orbit or lost communication during the journey. Engineers continued because Venus was nearby, offered frequent launch opportunities, and raised fundamental questions about a planet so similar to Earth in size. The American spacecraft Mariner 2 completed a successful flyby of Venus in December 1962. It was the first spacecraft to reach another planet successfully. Microwave measurements showed that the extreme heat came from the surface, not merely from a warm atmospheric layer. This ended popular ideas about tropical oceans or steaming swamps beneath the clouds. Before those measurements, several models imagined Venus as a wet world with jungles or shallow seas. Clouds were interpreted as evidence of water vapor, while proximity to the Sun suggested a hot but possibly tolerable climate. Mariner 2 showed that the clouds were not signs of an ocean below. The brilliant white appearance concealed an environment drier and hotter than optimistic predictions had allowed. The Venera program moved step by step into the atmosphere. Venera 4 in 1967 directly measured carbon dioxide and high pressure during descent. It did not survive to the surface because the environment was harsher than expected. The result forced later missions to use stronger pressure vessels and more powerful thermal protection. Venera 7 became the first spacecraft to transmit data from the surface of another planet in 1970. A weak signal continued after landing and confirmed the extreme temperature and pressure. The mission did not return a photograph, but it proved that human technology could reach the Venusian ground and continue to operate. Venera 9 and Venera 10 returned the first images from the surface in 1975. The photographs showed flat rocks, broken fragments, and a distant horizon under yellow-orange light. There were no flames, no rivers of acid, and no vegetation. There was only a rocky plain beneath a massive atmosphere. Venera 13 survived for more than 2 hours in 1982, returning color images, analyzing the soil, and recording environmental sound. Venera 14 performed similar measurements. In a famous incident, the protective cap from a soil compression instrument landed directly beneath the experiment arm, causing the device to measure the cap instead of the Venusian ground. This small accident is often told as a humorous story in the history of exploration, but it reveals the limits of remote operations. Every action had to be programmed in advance. No person could make a repair, and the spacecraft's remaining life was measured in minutes. One object falling in the wrong place could eliminate a measurement that might not be attempted again for decades. The American Pioneer Venus project arrived in 1978 with 1 orbiter and 4 atmospheric probes. The probes entered different regions, measuring temperature, pressure, clouds, and atmospheric composition. One small probe survived its impact and continued transmitting from the ground for more than an hour, even though it had not been designed as a lander. The Pioneer Venus orbiter operated for more than 13 years. It produced early radar maps, monitored the clouds, studied the ionosphere, and observed interactions with the solar wind. Its long record showed that the Venusian atmosphere changes with solar activity and established a foundation for later missions. The 2 Soviet Vega missions of 1985 combined descent probes with balloons. Each balloon floated at an altitude near 54 kilometers and traveled thousands of kilometers with the winds for almost 2 days. They measured temperature, pressure, light, and atmospheric motion, proving that vehicles can survive far longer in the cloud layer than on the surface. After releasing their Venus instruments, the Vega carrier spacecraft continued toward Halley's Comet. This design showed how one planetary encounter could serve several objectives. Venus is often used for gravity assists because its orbital motion allows spacecraft to change energy and direction without consuming an equivalent amount of fuel. Venera 15 and Venera 16 used radar to map much of the northern hemisphere. Magellan then provided the global breakthrough. Launched in 1989, it entered orbit the following year and used synthetic aperture radar to map about 98% of the surface. Magellan did more than create images. It measured elevation, radar reflectivity, and the gravity field. It also performed aerobraking, repeatedly entering the upper atmosphere to reduce and circularize its orbit. When the mission ended in 1994, the spacecraft was lowered to collect additional information about atmospheric density before contact was lost and it burned up. The Magellan Archive continues to produce discoveries more than 3 decades later. Modern computers, improved topographic maps, and new image comparison methods have revealed changing volcanic vents, fresh lava flows, and corona that may still be active. A completed mission remains a telescope into the past because its data can be examined with questions that earlier generations had not yet imagined. The European Space Agency's Venus Express entered orbit in 2006. It focused on the atmosphere, the plasma environment, and infrared observations of the night side. It monitored polar vortices, atmospheric escape, changes in sulfur dioxide, and thermal windows that provide limited views toward the surface. Venus Express found enhanced deuterium in the upper atmosphere and observed oxygen and hydrogen ions escaping into space. It also detected regions with unusual infrared emissivity, interpreted as either relatively young surfaces or rocks with different compositions. These measurements did not prove that an eruption was occurring, but they strengthened the case for ongoing geological activity. As its fuel supply declined, the mission team lowered Venus Express into the atmosphere to test aerobraking. The spacecraft directly measured upper atmospheric density before contact was lost in 2014. Like Magellan, the mission turned its final orbital decline into a scientific experiment. Japan launched Akatsuki in 2010 to study Venusian meteorology. Its first attempt to enter orbit failed because of an engine malfunction. The spacecraft then traveled around the Sun for 5 years before engineers used smaller thrusters, which had not been designed for the main maneuver, to make a second attempt. In December 2015, Akatsuki successfully entered orbit around Venus. The resulting orbit differed from the original plan, but it still allowed the spacecraft to observe the atmosphere at several wavelengths. The recovery became one of the most remarkable mission rescues in planetary exploration. Akatsuki monitored daytime clouds, heat from the night side, water vapor, carbon monoxide, and atmospheric motion. It discovered enormous mountain waves, studied the mechanisms that sustain superrotation, and built a long record of changing weather patterns. Its observations were also combined with meteorological models through data assimilation, a method widely used in weather forecasting on Earth. Communication with Akatsuki was lost in late April 2024 after a problem in its attitude control mode. Following repeated unsuccessful recovery efforts, the Japan Aerospace Exploration Agency officially ended the mission on September 18, 2025. Akatsuki had observed Venus from orbit for more than 8 years. The end of Akatsuki created a temporary gap, leaving no dedicated spacecraft operating around Venus. The planet continues to be studied with telescopes on Earth and during encounters by spacecraft traveling elsewhere. Bepi Colombo observed Venus during flybys on its journey to Mercury, while Solar Orbiter continues to use Venusian gravity assists to reshape its orbit around the Sun. Brief flybys cannot replace a long-lived orbiter, but they provide valuable additional perspectives. Instruments can sample the plasma environment, observe atmospheric structure, and measure how Venus interacts with the solar wind under conditions different from those seen by earlier missions. Ground-based telescopes continue to track clouds, trace gases, and small variations in rotation. The history of exploration shows that each kind of vehicle is suited to a different layer of the planet. Orbital radar reads the terrain, spectrometers analyze clouds and gases, descent probes measure composition with altitude, balloons follow the weather, landers touch the rock. No single mission can explain all of Venus. That is why the next generation of exploration is being designed as a set of complementary answers. One mission will descend deep into the atmosphere. Another will map the surface with a new radar system. A third will connect the core and mantle to geology and climate. After decades spent re-examining old data, humanity is preparing to return to Venus with more powerful tools. Da Vinci, whose full name is the Deep Atmosphere, Venus Investigation of Noble Gases, Chemistry, and Imaging mission, is designed to follow the planet from above the clouds to near the surface. A carrier spacecraft will perform flybys and observe the atmosphere and ground through selected wavelength windows. It will then release a spherical probe into the atmosphere. During a descent lasting about 1 hour, the probe will measure temperature, pressure, winds, noble gases, isotopes, and trace compounds. A vertical record is more valuable than one isolated measurement because it reveals where reactions occur, how gases mix, and which layers retain ancient signatures. Ratios involving xenon, krypton, argon, and deuterium may distinguish different histories of water and atmospheric origin. As the probe falls below the clouds, the Da Vinci camera will see Alpha Regio. These will be the first close views of a tessera region ever obtained by a descending spacecraft. If the slopes and rock layers show forms consistent with erosion, or if their composition is rich in silica, they could transform the debate over ancient water on Venus. The probe does not need to survive long after reaching the ground to complete its main objectives. Its greatest value lies in the continuous sequence of measurements made during descent. If the system remains functional at the surface, however, it will continue collecting data. Even a few additional minutes could provide images, temperature readings, and chemical information from the landing site. In June 2026, the Da Vinci team tested a prototype imaging system during helicopter flights over the Utah desert. The instrument was lowered across volcanic terrain to examine how images change with altitude, vibration, and lighting. These tests on Earth help create the algorithms that will turn descent images into a 3-dimensional map of Alpha Regio. The mission is currently planned for launch around 2029, although the exact schedule depends on development progress, and launch opportunities. When it reaches Venus, Da Vinci will be the first United States atmospheric probe at the planet in more than 4 decades, and the first spacecraft of the 21st century to descend beneath its cloud layers. Veritas, whose full name is Venus Emissivity, Radio Science, Interferometric Synthetic Aperture Radar, Topography, and Spectroscopy, will concentrate on the surface and interior. The orbiter is planned for launch no earlier than 2031. After arrival, it will use aerobraking to enter a low, nearly circular polar orbit. The Veritas radar will create 3-dimensional maps at much higher resolution than Magellan and will search for changes between repeated observations. Interferometric radar may detect ground movement caused by rising magma, fault motion, or deformation around coronae. Even small changes over time can leave measurable shifts in radar phase when observing conditions are favorable. A near-infrared emissivity instrument will investigate rock composition through atmospheric windows. The goal is to distinguish basalt, recently erupted material, and more silica-rich rocks. If the tesserae differ compositionally from the plains, the observations may reveal how the earliest Venusian crust formed. Radio tracking of Veritas will improve the gravity map. Combining gravity with topography will constrain crustal thickness, corona structure, and the support beneath mountain ranges. The data will also improve estimates of tidal response, helping scientists limit the size and physical state of the core. The European Space Agency's Envision mission is planned for launch in November 2031. After a journey of about 15 months, it will reach Venus and spend nearly a year using aerobraking to enter its science orbit. The main observation phase is expected to last about 4 Earth years. Envision is designed to study Venus as one connected system, a radar instrument provided by the National Aeronautics and Space Administration will map the surface and search for changes. Spectrometers will observe the atmosphere, clouds, minerals, and volcanic gases. A radio science experiment will measure gravity, the deep interior, and atmospheric structure. The 3 missions do not repeat the same task. Da Vinci will provide a direct chemical profile through the atmosphere. Veritas will focus on global mapping, topography, gravity, and deformation. Envision will connect geology and atmosphere across a long observational record. When their data are combined, an eruption might be recognized through radar changes, an infrared hotspot, and a fresh release of sulfur-bearing gas. Their coordination will also test the history of water. Noble gases and isotopes will reveal how much material the atmosphere has lost. Tessera composition will show whether water once affected the crust. Volcanic maps will record how gases were released through time. Climate models will use all of these measurements to reconstruct the states Venus may once have experienced. Future missions must also identify the ultraviolet absorber. Once its composition is known, scientists can calculate more accurately how much solar energy is absorbed in the clouds. The particles may also reveal whether sulfur, iron, or mineral dust rises from below. A mystery first seen as dark markings in an image may become the link between photochemistry and climate. The atmosphere below the clouds remains less well understood than many people assume. Older probes sampled only a few places and moments, never forming a global network. Winds, convection, atmospheric stability, and lower-level composition influence both heat transport and the rise of volcanic gases. Da Vinci will provide one extremely precise vertical profile, but future exploration will still require probes at other latitudes. A long-duration balloon may be the next step. Carried by super-rotating winds, it could circle the planet repeatedly while observing the clouds from within. It might change altitude to sample chemistry, listen for acoustic waves from earthquakes, and search for flashes if lightning exists. Acid-resistant materials and solar energy systems have advanced greatly, since the Vega missions. The surface requires a different technology. Conventional silicon electronics fail quickly at Venusian temperatures, but components made from silicon carbide and other heat-resistant materials may operate much longer. A small station without complex refrigeration could measure pressure, temperature, wind, seismic activity, and chemistry for months, transmitting data to a balloon or orbiter. A mission that collected rock and launched it back to orbit would be far more difficult. A rocket would have to endure heat and pressure before ignition, its propellant would need to remain stable, and the sample would have to pass upward through the dense atmosphere. Although this is not a near-term objective, returning tessera rock to a laboratory would permit isotopic dating and mineral identification with precision no remote instrument can match. Venus is also a testing ground for methods used to study exoplanets. We cannot send spacecraft to worlds orbiting other stars, so we must infer their nature from spectra and changing light. Venus provides local ground truth for testing whether a cloudy, carbon dioxide-rich, intensely hot planet can be recognized from far away. Many rocky exoplanets now known orbit closer to their stars than Venus orbits the Sun. Some are tidally locked, with one side always facing the star. Dayside clouds may reflect light and shift the inner boundary of habitability, much as some models propose for young Venus. A thick atmosphere can also carry heat into darkness and prevent an extreme temperature contrast. Not every Earth-sized exoplanet is a second Earth. Many candidates may instead be hot, dry, cloud-covered versions of Venus. Without understanding our nearest planetary neighbor, we may misjudge a world located dozens of light-years away. Venus also matters to Earth climate science, but the comparison must be made carefully. The modern greenhouse effect on Earth and the extreme state of Venus differ enormously in pressure, carbon dioxide abundance, water, clouds, and geological history. Earth is not about to become Venus simply because temperatures rise over several centuries. What Venus provides is a physical limit. It shows that planetary climates can occupy very different stable states and that feedbacks can amplify change. It reminds us that oceans, the carbon cycle, and the atmosphere do not exist independently. When one component changes enough, the entire system may move on to a different path. On Earth, human-driven climate change is a real problem on the scale of centuries, affecting temperature, sea level, extreme weather, and ecosystems. Venus is not a direct comparison, but it allows scientists to test models of radiation, clouds, and greenhouse gases under conditions too extreme to reproduce fully in a laboratory. Venus also raises a deeper question about the durability of habitability. If the planet possessed oceans for billions of years and then lost them, a world may remain temperate for a very long time before changing profoundly. If Venus never cooled, then small differences in early conditions may have determined its fate from the beginning. Both possibilities matter in the search for life beyond the solar system. In the very distant future, the Sun will grow brighter and push climatic boundaries farther outward through the solar system. Earth will eventually lose the conditions it has today, while Venus will receive still more energy. That era lies billions of years away. The urgent scientific task is not to predict the final scene, but to understand what happened in the past. Perhaps Venus once had seas, perhaps water survived only briefly, perhaps the tesserae are remnants of continent-like crust, or perhaps they formed entirely through compression and volcanism. Science has not chosen one story because crucial evidence is still missing. The mystery of Venus lies in the space between several histories that remain physically possible. What is certain is that Venus is not a dead world hidden beneath clouds. Old data show that volcanoes erupted while Magellan was observing the planet. Coronae appear to be deforming. The atmosphere continues its super-rotation, Mountain waves rise toward the cloud tops and material continues to escape into space. Venus is changing, even though most of that motion remains hidden from human sight. When we look at Venus in twilight, we see sunlight that has crossed space, reflected from clouds of sulfuric acid, and returned to Earth. That light carries no direct image of Maxwell Montes, Alpha Regio, or the long lava channels below. It tells us only that a planet is there, brilliant and reserved, keeping its entire surface behind a white curtain. For thousands of years, that curtain allowed people to imagine almost anything beneath it. Jungles, warm seas, deserts, volcanoes, and life all occupied the unknown at different times. Every mission has made the empty space smaller, yet each has opened deeper questions about water, carbon, crust, and time. Venus is not a failed copy of Earth. It is the complete result of a different planetary path. Calling it a hell describes a human reaction to its heat and pressure, but science must look further. Venus is a climate, geological and chemical system that has evolved for more than 4 billion years. The story, therefore, does not end by turning away from a hostile world. It ends with a question directed back toward the observer. Earth and Venus formed near one another, grew to similar sizes, and received material from the same disk of dust and gas. What allowed one planet to keep its water while the other lost nearly all of it? The answer does not lie in one factor. It lies in clouds, oceans, rocks, crustal motion, volcanic gases, and the changing light of the sun. Venus gives us one half of the comparison. The other half is directly beneath our feet. In the next episode, the journey will not begin by looking toward a distant point of light. It will begin with a world so familiar that we rarely stop to see it as a planet. It is a sphere with deep oceans, a thin atmosphere, a constantly moving surface, and life that has altered the air itself. After Venus, the question is no longer only why one world became so hot. The question is why Earth has preserved its delicate balance for so long.